In our previous few videos, we have been developing the notion of number systems, and we are gradually developing it from the beginning, where we started from natural numbers, then we studied about whole numbers, and then integers, and then ratio of two integers, hence the name rational numbers. And we also talked about irrational numbers in a video. But today we'd like to discuss this concept called decimals and where do they fit in. We all know about decimals since our childhood, right? We have been working with them for quite some time. But today we'll again revise a few concepts we learned early on, and hopefully we'll have a fairly intuitive idea of applying this further into just exploring, and let's begin. So say that I have 1 over 10. Well, from what we have studied till now, we know that this is a rational number, and its ratio of two integers, and the denominator is non-zero, so it's just a rational number. I am interested in the decimal expansion of this rational number. So what I do, since we have a number system of base 10, we saw that there are 10 symbols altogether, and we permute those 10 symbols to represent the number system. So I divide this rectangle into 10 pieces. Assume that this is 10 pieces. Please don't count, but I give you one piece of the whole rectangle that has been divided into 10, and then this for me represents 1 over 10, right? This is fairly intuitive to everyone, I think. And this I am defining it to be 0 point. So whatever number I write after the point, it will represent how many parts of 10 I am giving you. So this is 1 in this case. This should be read as, this whole thing is 1 notation, and it should be read as 1 over 10. It's the same as this fraction. So what if we had 1 over 2? Again, we have a decimal base of, we have the number system base of 10, so we'd like to continue that further. Again, I divide it into 10 rectangles, and I give you half of the rectangles. Well, this is half, I think. I don't think I have drawn 10 rectangles specifically, but fine. So this is, according to me, so these will be 5 rectangles out of 10. So this will be 0 point. So whatever I write after the decimal, that thing over 10 is what I'm trying to represent. So this is 5, and this should be read as 1 over 2. Again, this whole thing means 1 over 2, or you can think of it as 5 over 10, and hence it is equal to 1 over 2. So this we know, right? We have studied this exact explanation for the decimals long time ago, but today I'll hopefully extend this explanation to what is the decimal representation of 1 over 3 now. So again, what do? I take a rectangle, I divide it into 10 parts. So this time I'm going to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, I shouldn't have counted. So this will give me 10 rectangles, and I'll have to give you a third part of the rectangle. So I divide the whole thing into somehow 3 segments, and I give you one of those segments, and I'm interested in how much you get, how many parts of 10 you get. So this is 3 plus a little bit of this triangle, this rectangle, right? So this is 0.3, but not quite, because there's some a little part of the rectangle next to it still left in my approximate. So this is just an approximate result. So I'll say 0.3 is actually not quite 1 over 3. So what does this give us? Actually, it tells us that dividing the rectangle into 10 parts won't suffice. So these are 10 parts. So this is not just, it's just not enough. So what if I divide it into more number of parts? Say that I divide it into 100 parts. 1, 2, 3, 4, no, I'll not count it till 100. So say that I am dividing it into 100 parts. Well, why did I choose 100? Again, because since we have a base of 10 and we somehow we I'm somehow making you believe that whatever number you write after this point, it should be read as that number over 10. So hopefully carrying that pattern further, the next thing I'm gonna write here, you should read it as the whole thing divided by 100, because since it's of base 10, there are 2 digits, so there are 100. So this is all just intuition for you. I think you might have a better intuition than what I'm trying to explain, but this will also give you a good insight. Well, what do I do? Again, I divide this. I'm trying to represent 1/3, remember? So I'm dividing this into 3 segments again, just like before. This time, what do I get? I get 33 boxes given to me, and that won't be just quite enough, because a small part of this next box should also be included in my result. So this can be written as 0.33, like 33. So we don't say this, how we differentiate from normal numbers. We don't say 33 after the decimal point, we say 33. So 0.33 is, but it's still not quite 1/3. There needs to be more precision, there needs to be more amount of boxes divided. So continuing this process further and further and further, we see that we get 1/3 is equal to 0.33. 1000 boxes won't be enough, so again 3, 3, 3, 3, 3, 3. So it goes on forever and ever. So luckily for us, well, this is the representation for 1/3, but luckily for us, there's a simpler way of thinking about division of rational numbers. Do you remember? We know about something called long division, or Euclid's division, or Euclid's division algorithm. So all these are the same process actually. So what if we divide, since I did it for 1/3 already, and you can do it for any other number also, for 1/2, 1/10, we have modified the Euclid's division in such a way that we also inculcate decimals in that, and you must already know to divide, I think. So let me try and show you what we get on dividing 1/7. And this would give, so now let us just divide. I'll write it as 0 point, I know it's 0 point something, because 7 doesn't go into 1, so it might go into 10, right? So 0.1s are 7, 3, again we can put a 0, and then it is 4s are 28. So this is just the procedure I am following for long division. You guys might be quicker than me in this. I encourage you to try. So 1, 4, 2, 14, and I have 6, 0, and well, 8s are 56, 7 8s are 56, 4, 0, and well, 4, 0, and 2, 7, is it 7, 4, 7, 5s are 35, and we have 5, 0, and 7. I know it will stop because it's a ratio, but well, so 7, 6 are, oh, 7 sevens are, sorry, 7 sevens are, and here we have 7 sevens are 49, and 1, 0, and well, we got 1, 0 over here. So if we just continue this further, we'll get the same 1, 4, 2, 8, 5, 7, and then again 1, 4, 2, 8, 5, 7. So this whole pattern would go on forever, right? So this is the decimal representation of 1/7. So I can write this as 1/7 is equal to 0.142857, and to show that it's repeating again and again, it's recurring, I'll just put a dash over this whole set of numbers, suggesting that it's repeating over and over again. So ultimately, what's the takeaway? This method, this long division method, is actually an outcome of this rectangle division thing we saw earlier. It's just a procedure given without actually dividing rectangles, we'd be able to find the decimal expansion. But this procedure can be expanded to any a by b whatsoever, any a by b you could think of. As long as the b is not 0, you can divide a by b using this method. You can put a point, you can divide it for however long you want, and you'll get a decimal representation of this fraction. So I just proved to you that all rational numbers, all a by b's, have a decimal representation. So this was the motive of the whole video, and in further few videos we see that how this decimal representations lead us magically to irrational numbers. So since then, take care. Thank you.